Let there be light, the illusions of cosmology and the truth of creation. Hello, dear listeners. Today we live in an age of scientific omnipotence. When we turn on the television, astrophysicists appear with confidence, announcing that they have accurately calculated the age of galaxies hundreds of billions of light years away. They definitively state that the universe is exactly 13.8 billion years old, and the Big Bang Theory is presented in textbooks as if it were a fact we directly witnessed. Evolution is accepted as scientific truth, and doubting it is dismissed as ignorance. But wait, is this really the case? What exactly is the basis for all this confidence? Let's face reality. Humans have only been to the moon a few times. From 1969 to 1972, through the Apollo missions, only 12 humans stepped foot on the lunar surface. The moon is merely 380,000 kilometers away from Earth. This is only about 10 times the circumference of Earth. Humans haven't even been to Mars yet. We've only sent a few robotic probes. Mars is 55 million kilometers away, even at its closest approach to Earth. Going near the Sun is completely out of the question. The Parker Solar Probe holds the record for the closest approach to the Sun, and even that only reached 6.9 million kilometers from the solar surface. Let's understand the scale of the universe. The distance to the nearest star, Proxima Centauri, is 4.2 light years. 1 light year is the distance light travels in 1 year, approximately 9.5 trillion kilometers. That means even the nearest star is about 40 trillion kilometers away. Let me explain this with a proportional analogy. If we shrink Earth to the size of a ping pong ball, the moon would be about the size of a marble 1 meter away. The sun would be the size of a soccer ball about 100 meters away. And the nearest star would be an incredible 30,000 kilometers away. This is more than twice Earth's diameter. Currently, the range humans have directly explored is only about a 1.5 meter radius around that ping pong ball in this analogy. Yet we claim to know the exact distance, age, and composition of celestial bodies 30,000 kilometers away, or even hundreds of millions or billions of times farther. The foundation of all this knowledge is light. We can only observe the universe through light, specifically electromagnetic radiation. Electromagnetic waves are oscillations of electric and magnetic fields propagating through space. The visible light we see is one type of electromagnetic wave, as are radio waves, infrared, ultraviolet, X-rays, and gamma rays. The problem is that these light rays take enormous amounts of time to travel from distant parts of the universe to reach us. The speed of light is approximately 300,000 kilometers per second, considered the fastest speed in the universe, but it's still slow compared to the vast scale of the cosmos. Here lies a fundamental problem. What we see is not the present, but remnants of the past. When we look at stars in the night sky, we have no idea what state those stars are in at this very moment. What we see is only light that star emitted at some point in the past. Take the sun as an example. It takes about 8 minutes and 20 seconds for light to travel from the sun to Earth. So the sun we see now is what it looked like 8 minutes and 20 seconds ago. If the sun suddenly disappeared right now, we wouldn't know for another 8 minutes and 20 seconds. This applies to all celestial bodies in the universe. Light from Proxima Centauri departed 4.2 years ago. Light from Sirius departed 8.6 years ago. Light from the North Star departed an incredible 433 years ago. The North Star we see now is from the time of King Seonjo during Korea's Joseon dynasty. What about more distant objects? Light from the Andromeda Galaxy departed 2.54 million years ago. This is light from the era when our ancestors, Homo habilis, lived. The most distant galaxies currently observed are estimated to be over 13 billion light-years away. This means the light from them departed over 13 billion years ago. Here comes the crucial question. What can we know about the current state of the universe? The answer is surprisingly, almost nothing. Everything we observe is only information from the past, and we can't even know exactly when that past was. Furthermore, we cannot be certain whether the speed of light has always been constant, whether light hasn't changed while traveling through cosmic space, or whether the characteristics of space itself haven't affected light. All of these are merely assumptions. Yet modern science insists on these uncertain assumptions to definitively state that the universe is 13.8 billion years old and demands we accept the Big Bang theory as fact. This is not science but belief, or rather blind faith. This audiobook is a journey toward breaking free from such blind faith and pursuing genuine truth. We will systematically deconstruct the premises that the modern scientific community takes for granted and present a completely different perspective on the universe and creation. This is not simple scientific criticism. It is an honest and humble inquiry toward truth. Chapter 1. The Bondage of Light. The Fundamental Limits of Observation. When we look up at the night sky and see stars, what are we actually seeing? Most people think they're seeing stars that are there now. But this is a complete illusion. We are only seeing light that those stars emitted at some point in the past. Let me explain this more specifically. Light propagates through space in the form of waves. This phenomenon, called electromagnetic waves, is the movement of electric and magnetic fields, oscillating perpendicular to each other through space. It's similar to ripples, spreading when you throw a stone into a pond. But unlike water waves, electromagnetic waves can propagate through vacuum without needing matter. The speed of light in vacuum is approximately 300,000 kilometers per second. This is an incredible speed that could circle Earth 7.5 times in 1 second. But even this speed is still slow compared to the scale of the universe. Even our solar system alone has a distance of about 4.5 billion kilometers to Neptune. It takes light about 4 hours to travel from the Sun to Neptune. But our galaxy has a diameter of 100,000 light years. 1 light year is the distance light travels in 1 year, approximately 9.5 trillion kilometers. This means it would take light 100,000 years to cross our galaxy from one end to the other. The nearest other galaxy, Andromeda, is 2.54 million light-years away. The edge of the currently observable universe is estimated to be about 46.5 billion light-years away. This is a much greater distance than the universe's age of 13.8 billion years according to Big Bang theory, explained by the fact that the universe continues to expand. To help understand, let me give examples of several familiar stars. 1. North Star. Located in the direction Earth's rotational axis points, it's 433 light-years away. The light we see from the North Star now departed around 1590, during the 23rd year of King Seonyo's reign in the Joseon dynasty. This is light from 2 years before the Japanese invasions of Korea. 2. Vega. Also called the Weaver Star, this star is 25 light-years away. The light we see from Vega now departed around 1998. 3. Rigel. A bright star in Orion, about 860 light-years away. The light we see from Rigel now departed around 1163, during the 17th year of King Uijong of Goryeo. 4. Deneb. The tail star of Cygnus, about 2,600 light-years away. The light we see from Deneb now departed around 577 BC, during the era of King Pyongwon of Goguryeo. Thus, all the stars we see are appearances from different eras. It's as if we're time traveling simultaneously viewing various points in the past. Do you understand? What I've just told you is that what we actually see when we look at the sky are different time periods from the past. That is, we are viewing the universe from different past time periods from a position in eternity, not the present. Different past time periods depending on distance, from the eternal past to the present, that we perceive with our eyes. It's just that the observer themselves, due to lack of cognitive ability, fails to realize this. What all this means is clear. We can know virtually nothing about the current state of the universe. Everything we observe is only information from the past. For example, the star Betelgeuse is about 700 light-years away and is expected to eventually undergo a supernova explosion. But this star may have actually already exploded 700 years ago. We just don't know it yet. Conversely, some of the bright stars we see now may actually already be dead and no longer exist. This is like trying to understand current situations by reading only old newspapers. It's as absurd as trying to analyze South Korea's current political situation by reading a 1920 edition of the Chosun Ilbo. All calculations in modern physics begin with the premise that the speed of light in vacuum is always constant. This is one of the basic assumptions of Einstein's special theory of relativity. But how has this premise been verified? Surprisingly, this is merely the extrapolation of results measured in Earth's laboratories to the entire universe. In 1983, the International Bureau of Weights and Measures defined the speed of light as exactly 299,792,458 meters per second based on measurements conducted on Earth. But cosmic space is a completely different environment from Earth's laboratories. First, the influence of gravitational fields. According to Einstein's general theory of relativity, time slows down and space curves in strong gravitational fields. Near black holes, time flows almost as if stopped, and even light cannot escape. Wouldn't light's speed or characteristics change as it passes through strong gravitational fields? Second, the influence of interstellar matter. Cosmic space is not a perfect vacuum. Various materials like interstellar dust, gas clouds, and plasma are sparsely distributed. Light could change in speed or wavelength through interactions with these materials. Third, the influence of magnetic fields. Powerful magnetic fields exist in the universe. Celestial bodies like pulsars, neutron stars, or magnetars have magnetic fields trillions of times stronger than Earth's magnetic field. Such strong magnetic fields could affect light propagation. Fourth, dark matter and dark energy. According to current cosmology, over 95% of the universe consists of invisible dark matter and dark energy. If these actually exist, how would they affect light propagation? We know nothing about this. A more fundamental problem is change over time. We know nothing about the changes light might have undergone during its journey of billions of years through cosmic space. Hypotheses have been proposed that physical constants change over time. Research results suggest that the fine structure constant, called a fundamental physical constant, may have changed slightly throughout cosmic history. If fundamental physical constants have changed, the speed of light could have changed too. Here, let me add a somewhat cynical perspective. Modern astrophysicists observe the universe from Earth, a tiny point, yet act as if they were omniscient observers. This is like an ant coming out of its anthill and claiming it can accurately measure the height and age of distant mountains. What's more problematic is that these speculations are packaged as scientific facts and delivered to the public. Uncertainties and assumptions are hidden, presented as if they were directly measured, reliable data. Instead of expressions like estimated to be or likely to be, they use definitive expressions like is or has been discovered to be. When you watch science documentaries, they show elaborate computer graphics, along with images of the Big Bang or black holes as if they were actually filmed. But these are all imagination based on theory. Most actual observational data consists only of black and white dots or waveform graphs. A truly scientific attitude should start by acknowledging the limits of observation. We need humility to recognize that we can only observe the universe through light, a very limited means, and even that is only information from the past. When Galileo discovered Jupiter's moons with his telescope, he only reported what he saw. He recorded only the observational fact that 4 small celestial bodies were orbiting Jupiter. He didn't infer the structure of the entire universe from that. But modern astronomy is different. It tries to reconstruct the entire history and future of the universe from limited observational data. This is like trying to explain an entire ocean's ecosystem with a few seashells picked up on a beach. This isn't a call to abandon science. Rather, it's about honestly acknowledging science's limitations and carefully drawing conclusions within that scope. Claiming speculation beyond the observable range as certain fact is not science but belief, or rather blind faith. The means by which humans can observe the universe are extremely limited. Besides electromagnetic waves, light, gravitational waves, and cosmic ray observations are possible, but these also provide very limited information. Gravitational waves were first directly observed in 2015. Through a device called LIGO, Laser Interferometer Gravitational Wave Observatory, they detected gravitational waves from black hole collisions. But the information obtainable from gravitational wave observations is very limited, and much less than electromagnetic wave observations. Cosmic rays are high-energy particles flying from space. These also provide some information about the universe, but it's also limited. Moreover, it's difficult to know exactly where these particles came from or when they departed. Ultimately, over 99% of our knowledge about the universe depends on observations through light. But even that light is information from the past, and we don't know how many changes it underwent while traveling through cosmic space. This is like exchanging only letters to check on a foreign friend's well-being. We have no idea what happened during the time it takes for letters to arrive. Moreover, the content could be altered during delivery. Acknowledging the fundamental limits of cosmic observation through light is the starting point of a truly scientific attitude. We are only seeing remnants of the past, not the current universe, and we can't even be certain how accurate even that is. Based on such humility, a completely different approach to the origin and age of the universe becomes possible. The possibility opens to interpret current observational data from different perspectives, and alternative hypotheses like instantaneous creation can be seriously considered. Chapter 2: The Illusion of Time: Errors in Measuring the Universe's Age. What is the basis for modern cosmology's claim that the universe is 13.8 billion years old? Mainly 3 things: the distance to the most distant objects, the rate of cosmic expansion through the Hubble constant, and the age of the oldest stars. But underlying all these calculations is the assumption that time flows uniformly throughout the universe. But is time really absolute and uniform? Before exploring this, let's first think about what time is. In daily life, we take time for granted. We check clocks to see what time it is, thinking a day is 24 hours and a year is 365 days. But the nature of time is not so simple. Let's look at methods for measuring time. In ancient times, people used sundials or water clocks. They divided a day into 24 hours using Earth's rotation and defined a year using Earth's revolution. Currently, we define 1 second based on cesium atom oscillations. Specifically, 1 second is defined as the time it takes for 9,192,631,770 cycles of radiation, corresponding to a specific transition in the ground state of the cesium-133 atom. But all these definitions were made on Earth, in Earth's environment. Would these definitions apply identically in other environments in the universe? Einstein's theory of relativity, announced in the early 20th century, completely changed our understanding of time. According to relativity, time is not absolute. The flow of time varies depending on the observer's state of motion and the strength of the gravitational field. Special relativity states that time slows down for rapidly moving objects. This is called time dilation. For example, in a spacecraft moving at 90% the speed of light, time flows about 2.3 times slower. That is, while 1 year passes in the spacecraft, 2.3 years pass on Earth. General relativity states that time slows down in strong gravitational fields. This is called gravitational time dilation. At higher altitudes than Earth's surface, gravity is weaker, so time flows slightly faster. This difference is very small, but actually measurable. These phenomena are not theories, but actually measured facts. 1. GPS satellites. GPS satellites orbit about 20,000 kilometers above Earth's surface. At this altitude, gravity is weaker than at Earth's surface, so time flows faster, about 45 microseconds faster per day. Also, since satellites move rapidly at 3.9 kilometers per second, time dilation due to special relativity also occurs. This causes about 7 microseconds of slowdown per day. As a result, GPS satellite clocks run about 38 microseconds faster per day than clocks on Earth's surface. Without correcting this difference, GPS errors would accumulate by about 11 kilometers per day. The GPS system actually operates by precisely correcting these relativistic effects. 2. Particle accelerator experiments. In high-energy particle accelerators, particles accelerated to near light speed are actually observed to have slowed time. A particle called a muon decays on average after 2.2 microseconds when at rest, but survives much longer when moving rapidly. 3. Atomic clock experiments. When precise atomic clocks are flown on aircraft, and then compared with ground-based atomic clocks, time differences are actually measured. In the 1971 experiment by Huffell and Keating, results were obtained that exactly matched relativity theory predictions. Now let's think about these effects on a cosmic scale. The universe contains gravitational fields incomparably stronger than Earth's. First, black holes. Black holes are celestial bodies with gravity so strong that even light cannot escape. Near black holes, time slows down extremely. Near a black hole's event horizon, time flows almost as if stopped. In the movie Interstellar, the protagonists spend 1 hour on a planet near a black hole, but 7 years pass on Earth. While this is exaggerated, such extreme time dilation is actually possible in strong gravitational fields. Second, neutron stars. Neutron stars are celestial bodies where matter equivalent to 1.4 to 2 times the Sun's mass is compressed into a sphere about 20 kilometers in diameter. Their surface gravity reaches billions of times Earth's. Time slows considerably on neutron star surfaces. Third, massive black holes at galactic centers. At our galaxy's center is a massive black hole equivalent to 4 million solar masses. Time dilation due to strong gravity occurs around this black hole. What effect have such extreme gravitational environments had on time's flow during the universe's 13.8 billion year history? The early universe was much denser than now. According to Big Bang theory, all matter in the early universe was in an extremely compressed state. In such high-density environments, gravity would have been much stronger than now, so time's flow would also have been different from now. Furthermore, different regions of the universe have different matter distributions. so gravitational field strengths would also differ. Time's flow could be different in regions where galaxy clusters are concentrated versus nearly empty void regions. The evidence currently presented for cosmic expansion in cosmology is the redshift phenomenon. Light from distant galaxies is shifted toward the red side. Redshift is the phenomenon where light's wavelength becomes longer. When wavelength increases, light appears redder. Blue light has a wavelength of about 400 to 500 nanometers, and red light has a wavelength of about 600 to 700 nanometers. So when wavelength increases, it shifts from blue to red. Currently, this is mainly interpreted as the Doppler effect. The Doppler effect is the phenomenon where frequency changes when the source of sound or light moves relative to the observer. When an ambulance approaches, its siren sounds higher, and when it moves away, it sounds lower. This is an example of the Doppler effect. Interpreting distant galaxies' redshift as the Doppler effect leads to the conclusion that those galaxies are moving away from us. More distant galaxies have greater redshift, so they're interpreted as moving away faster. This is considered evidence of cosmic expansion. But is the Doppler effect really the only cause that can explain redshift? Number. There are several other causes that could produce redshift. 1. Gravitational redshift. Light, coming from strong gravitational fields, shows redshift by losing energy. Light loses energy as it escapes gravitational wells when leaving gravitational fields. Light from the Sun also shows weak gravitational redshift. If distant galaxies are surrounded by strong gravitational fields we don't know about, light from them could show redshift. If dark matter really exists, its gravitational effects could influence light. 2. Tired light hypothesis. Light could lose energy while traveling long distances. This is called the tired light hypothesis. Light could lose energy through interactions with particles in cosmic space or through unknown mechanisms. 3. Characteristics of cosmic space itself. Cosmic space itself could affect light wavelength. According to quantum field theory, even vacuum is not completely empty, but is active space where virtual particles repeatedly create and annihilate. Such quantum fluctuations could affect light propagation. 4. Changes in physical constants. If physical constants change over time, redshift could appear. For example, if the fine structure constant was different in the past than now, atomic energy levels would have been different, so the wavelength of emitted light would also have been different. Hubble's law, which shows the relationship between redshift and distance, is also being found to have several problems. Hubble's law represents the observational fact that more distant galaxies have greater redshift. But this law has considerable scatter. That is, galaxies at the same distance often show different redshifts. Also, some objects show much greater redshift than expected, or even show blue shift. Some quasars show redshift too large for their distance. Cases have also been discovered where objects that appear to be gravitationally connected show completely different redshifts. The Hubble constant itself gives different values depending on the measurement method. Methods using Cepheid variables and methods using cosmic microwave background radiation show statistically significant differences. This is called Hubble tension. Here, let me add a somewhat cynical perspective. Modern astrophysics has introduced new hypotheses whenever observational results don't match their theories. When galaxy rotation speeds are faster than expected, they assume dark matter. And when cosmic expansion accelerates, they assume dark energy. Currently, they claim over 95% of the universe consists of such invisible things. This is like continuously adding invisible variables to force calculations to match when your calculations are wrong. Wouldn't it be more scientific to think that the initial premise might be wrong? Also problematic is the authoritarian structure of the scientific community. Research challenging mainstream theories has difficulty receiving research funding and getting papers published. Non-mainstream theories are often rejected from the start. Time may be a concept that only has meaning within our human experience range. Carelessly estimating time on a cosmic scale, especially time before creation, may be arrogance beyond human limitations. Current calculations of the universe's age as 13.8 billion years are based on the following assumptions. The Hubble constant is accurate. The universe is actually expanding. Redshift is due to the Doppler effect. Physical laws were the same in the past. Time has flowed uniformly throughout the universe. If any of these is wrong, the universe's age calculation could be completely incorrect. Especially the fifth assumption of time uniformity has already been negated by relativity theory. If there were extreme gravitational environments in the early universe, time's flow would have been completely different from now. Big Bang theory itself assumes that early universe density was close to infinite. What would time's flow have been like in such an environment? Furthermore, if the universe was created instantaneously, time itself would have been created at that moment. Then the concept of time before creation would become meaningless. Time is not as simple and absolute as we think. As relativity theory has shown, time is relative, varying with observer and environment. Claiming to know the universe's age precisely may be human arrogance. How can we claim to accurately calculate the entire universe's time when we don't even fully understand the nature of time? A truly scientific attitude is to acknowledge such uncertainties and approach humbly. Current calculations of the universe's age are only one hypothesis, and we should have an open mind that completely different interpretations are possible. Chapter 3. The Mirage of Distance, Uncertainties in Cosmic Surveying. The distance from Earth to Sol can be easily known from highway signs, but measuring distances in the universe is a completely different order of problem. We can't go there and measure with a tape measure, nor can we use radar or GPS. We can only estimate distances through light. The method astronomers use to measure cosmic distances is called the cosmic distance ladder. This is a method that starts from nearby distances and gradually extends to farther distances, like climbing a ladder one step at a time. But the fundamental problem with this method is that errors from each step accumulate. If there's a 10% error in the first step, there could be hundreds of percent error in the final step. The most basic distance measurement method is triangulation. This uses the principle of trigonometry learned in high school mathematics. As Earth orbits the Sun, after 6 months, it's positioned on the opposite side. At this time, Earth's position change is about 300 million kilometers, the diameter of Earth's orbital path. Using this distance as a baseline, we can calculate distance by measuring a star's position change. The closer a star is, the larger its position change appears. This is called annual parallax. 1 parsec is the distance where annual parallax is 1 arc-second, equivalent to about 3.26 light-years. But the distance measurable by this method is very limited. With ground-based telescopes, accurate measurements were only possible up to about 100 parsecs, about 326 light-years. The European Space Agency's Hipparcos satellite, operated from 1989 to 1993, performed more precise measurements. This extended the measurement range to about 1,000 parsecs, 3,260 light-years. The Gaia satellite, operated since 2013, performs even more precise measurements, extending the measurement range to tens of thousands of parsecs. But considering that our galaxy's diameter is 100,000 light-years, about 30,000 parsecs, direct measurement is only possible within about 30% of the galaxy. For more distant measurements, where direct measurement is impossible, indirect methods must be used. The most important among these is the method using variable stars. Cepheid variables are stars that periodically change brightness. What's important is that there's a definite relationship between their variation period and absolute brightness. Cepheids with longer periods are brighter. In 1912, Henrietta Leavitt, Hubble's colleague, discovered this relationship while studying Cepheid variables in the Magellanic Clouds. Stars in the same galaxy can be assumed to be at nearly the same distance, so differences in observed brightness reflect differences in actual brightness. By observing a Cepheid's variation period, we can know that stars' absolute brightness. Comparing absolute brightness with observed brightness allows us to calculate distance. This is the same principle as calculating distance from actual brightness when you know a light bulb's wattage. But this method also has several problems. First, the period-luminosity relationship itself is based on distances to nearby Cepheids obtained in the first step, so errors from the first step are directly reflected. Second, there are several types of Cepheids, each with different characteristics. Population 1 and Population 2. Cepheids have different brightness even with the same period. Failing to distinguish these causes errors in distance calculations. Third, absorption and scattering by interstellar dust must be accurately corrected. Dust absorbs blue light especially, making stars appear dimmer and redder than they actually are. Failing to correct this accurately can lead to incorrect distance calculations. For even more distant measurements beyond Cepheid range, Type Ia supernovae are used as standard candles. Type Ia supernovae are explosions that occur when a white dwarf steals matter from a companion star and reaches a certain mass. Theoretically, they always explode at the same mass, so they should have similar brightness. In reality, Type Ia supernovae have quite uniform peak brightness. Moreover, analyzing the shape of light curves allows more accurate estimation of absolute brightness. There's a rule that supernovae that dim slowly are brighter. Type Ia supernovae can be bright enough to outshine entire galaxies, so they can be observed at very great distances. The most distant supernovae observed so far have redshifts greater than 1.7, from about 30% of the universe's age. But Type 1a supernovae also have problems. First, it's uncertain whether all Type Ia supernovae actually occur through the same mechanism. Cases where white dwarfs slowly accumulate matter and explode may differ from cases where two white dwarfs collide and explode. Second, there's the possibility of change over time. Stars in the early universe had different chemical compositions from current stars. Did white dwarfs in the early universe, with lower ratios of heavy elements, explode in exactly the same way as current ones? Third, as distance increases, it becomes harder to observe individual supernovae in detail. Distant supernovae may be buried in their surrounding galaxy's brightness, making accurate brightness measurements difficult. Other additional distance measurement methods are as follows. 1. Surface brightness fluctuation method, a method that analyzes brightness fluctuations on galaxy surfaces to measure distance. Closer galaxies can resolve individual stars, so surface brightness fluctuations are larger. 2. Tully-Fisher relation, a method using the relationship between spiral galaxies' rotation speeds and absolute brightness. Faster rotating galaxies are brighter based on this empirical relationship. Third, gravitational lensing effect uses the phenomenon where light from distant quasars is bent by gravity from intervening galaxies, appearing as multiple images. Analyzing the time differences in brightness changes of each image allows distance calculations. And systematic errors in distance measurements are as follows. 1. Personal bias. In the past, individual astronomers used different distance scales. Some thought the universe was larger, others thought it was smaller. Such biases influenced measurements. Second, selection effects. Bright objects are more easily observed, creating bias in samples. Also, particularly bright or unusual objects tend to be studied more. 3. Systematic instrumental errors. Telescope or detector characteristics can cause consistent directional errors. Early photographic plates especially had limited accuracy. Here, let's examine measurements and interpretations of cosmic microwave background radiation. The cosmic microwave background radiation, CMB, discovered by Penzias and Wilson in 1965, is currently considered the strongest evidence for Big Bang theory. This is 2.7 K temperature microwave radiation, observed uniformly across the entire sky. According to current cosmology, the CMB is light emitted when the universe cooled sufficiently, about 380,000 years after the Big Bang, for neutral atoms to form. Until then, the universe was in a plasma state where light couldn't propagate freely, but it suddenly became transparent when recombination occurred. Through observations by COBE, WMAP, Planck satellites and others, minute temperature variations in the CMB have been discovered. These variations are very small, about 1 part in 100,000, but are interpreted as seeds of the current universe's large-scale structure. But CMB interpretation also has several problems. First, the horizon problem. According to the Big Bang model, distant regions that couldn't be causally connected have very uniform temperatures. Cosmic inflation hypothesis was introduced to explain this, but this itself is unverified speculation. Second, the monopole problem. Grand unified theories predict magnetic monopoles should have been created in the early universe, but they're not actually observed. Third, the flatness problem. The current universe's geometric structure is nearly flat, which is only possible with extremely precisely tuned initial conditions. Now let's look at the Hubble constant dilemma. The Hubble constant represents the speed of cosmic expansion. The problem is that Hubble constant values measured by various methods don't match each other. This difference is about 8 to 9%, beyond measurement error ranges. This is called Hubble tension, and is one of current cosmology's biggest challenges. If we don't know the Hubble constant accurately, how reliable can universe age calculations be? If the Hubble constant is wrong by 10%, the universe's age could also be wrong by 10%. More fundamentally, this discrepancy could be a sign that current cosmological models themselves have problems. Perhaps the universe operates in completely different ways than we think. Here, let me add a somewhat cynical perspective. The astronomical community has modified existing theories whenever observational technology advances. When the Hubble Space Telescope was introduced, and when the James Webb Space Telescope began observations, results different from previous expectations emerged. But each time, instead of questioning fundamental premises, they've responded by fine-tuning theories. This is like getting lost with the wrong map and assuming there are new shortcuts whenever the path doesn't match, rather than fixing the map. They continue adding unverifiable concepts, like dark matter, dark energy, and cosmic inflation, to maintain existing theories. Also, distance measurement uncertainties are rarely mentioned. Scientific papers often present only statistical errors, not adequately addressing systematic errors or model dependencies. Public announcements are even more definitive. Accurately measuring cosmic distances is very difficult with current human technology levels, especially for extremely distant measurements like intergalactic distances. Our measurement methods depend too heavily on assumptions and inferences. If each step of the cosmic distance ladder has 5 to 10% error, the final step could have tens of percent error. This is a mathematically unavoidable problem. Distance measurement depends on understanding celestial objects' physical properties. If we misunderstand the nature of Cepheids or supernova, distance calculations could also be wrong. If the universe's physical conditions changed over time, past objects may have had different characteristics from current ones. In this case, applying current empirical laws to the past could be inaccurate. Considering these limitations, completely different interpretations of cosmic distance and size may be possible. What if the universe is much smaller than currently thought? Or what if basic assumptions of distance measurement are wrong? It's time to seriously consider these possibilities. Especially when considering instant creation hypotheses, current distance measurement methods could have completely different meanings. The distances we measure might not be actual physical distances, but information patterns set at the moment of creation. Cosmic distance measurement is a representative case showing current science's limitations. Depending on indirect methods in areas where direct measurement is impossible, inevitably creates much uncertainty. Acknowledging these limitations and honestly expressing uncertainties associated with distance measurements would be a more scientific attitude. Rather than definitive claims about cosmic size and age, clarifying the limits of what we can currently know is necessary. Chapter 4. The Mystery of Matter, the Ocean of the Unknown. We don't even properly understand atoms, considered the most basic units of matter. In daily life, matter feels solid and certain. But when we look into the microscopic world, it's full of mysteries and contradictions. Atoms consist of a nucleus at the center and electrons orbiting around it. The nucleus is made of protons and neutrons, and electrons carry negative charge. But even this simple explanation carries many problems. The nucleus size is about 100,000th of the entire atom's size. If we enlarged an atom to stadium size, the nucleus would only be about the size of a marble in the center. Then most of the atom would be empty space. So why does matter feel solid? According to classical physics, charged particles undergoing accelerated motion should emit electromagnetic waves and lose energy. If electrons orbit the nucleus, they should continuously lose energy and eventually fall into the nucleus. But this doesn't actually happen. Why? To solve these problems, quantum mechanics emerged in the early 20th century. According to quantum mechanics, electrons don't orbit in fixed paths, but exist probabilistically. Heisenberg's uncertainty principle applies, stating we cannot simultaneously know an electron's position and momentum precisely. But do these explanations really represent physical reality, or are they merely mathematical tools? Einstein refused to accept quantum mechanics' probabilistic interpretation, saying, God does not play dice. The force that holds protons and neutrons together in the nucleus is called the strong nuclear force. Protons all carry positive charge, so they electrically repel each other. But the strong nuclear force overcomes this electrical repulsion to keep the nucleus stable. But what exactly is this strong nuclear force? According to current theory, particles called gluons carry this force. But gluons have never been directly observed. According to quark theory, protons and neutrons consist of smaller quarks, and gluons bind quarks together. Quarks cannot exist individually and are always found bound together. This is called quark confinement. The more you try to separate quarks, the stronger the force becomes, like stretching a rubber band. But why is this so? There's no fundamental explanation for this. Current theories only describe phenomena, but don't provide fundamental reasons for why such phenomena occur. Electricity and magnetism are phenomena indispensable to our daily lives. Electronic devices, motors, generators, everything uses electromagnetic phenomena. But what exactly electric and magnetic fields are and why they exist remains mysterious. Maxwell's equations formulated by Maxwell in the 19th century perfectly describe electromagnetic phenomena mathematically. These equations could predict the existence of electromagnetic waves and showed that light is also a type of electromagnetic wave. But the concept of fields, described by these equations, is abstract. There's disagreement about whether electric fields are actual physical entities existing in space or merely mathematical convenience tools. In quantum mechanics, electromagnetic force is explained as being carried by particles called photons. Electrons feel electromagnetic force by exchanging photons, but photons are massless and always move at light speed. How do we explain electrostatic force between stationary charges? How can stationary electrons exchange photons? There are no clear answers to these questions. Newton discovered the law of universal gravitation, but couldn't explain what gravity is. He himself said, "I frame no hypotheses about gravity's cause. Why do materials attract other materials? Why is gravity stronger with greater mass? How is gravity transmitted instantaneously through vacuum?" Newton couldn't find answers to these questions either. Einstein explained gravity as space-time curvature in general relativity. Matter, with mass curves space-time, and other matter moves along this curved space-time. This is a very elegant geometric explanation, and many predictions have been confirmed by observations. Mercury's perihelion precession, light bending, and gravitational wave existence are examples. But this doesn't explain gravity's essence either. There's still no fundamental explanation of what exactly spacetime is, or why mass curves spacetime. Like other forces, there's a hypothesis that gravity is also carried by particles called gravitons. But gravitons haven't been discovered yet, and there are many theoretical problems. Attempts to unify quantum mechanics and general relativity continue, but haven't succeeded yet. String theory, loop quantum gravity theory, etc. are proposed, but they're all unverifiable speculations. Einstein's famous equation shows that matter and energy can convert into each other. Mass is a form of energy, and energy can become mass. Atomic bombs and nuclear power plants use this principle. When uranium or plutonium nuclei split, part of the mass converts to energy. The sun also emits energy equivalent to mass loss, as hydrogen fuses into helium. But there's still no fundamental explanation of what exactly mass is or what exactly energy is. We only describe phenomena, but don't understand essence. According to quantum mechanics, all matter has wave properties. Electrons can behave like waves, and theoretically even soccer balls or cars have wave properties, though wavelengths are too short to observe. In double-slit experiments, even shooting electrons one by one produces interference patterns. Electrons behave as if they simultaneously pass through both slits, but when observed, electrons behave like particles. This completely overturns our common sense. What does it mean that matter behaves differently, depending on whether it's observed? According to quantum field theory, vacuum is not completely empty space. It's active space where virtual particles are constantly created and annihilated. The Casimir effect is actual evidence of such quantum fluctuations. Between two metal plates placed very close together, a force acts to pull the plates together. This is explained as there being fewer virtual particles between the plates than outside, but the concept of virtual particles itself is hard to understand. Do they actually exist, or are they just mathematical techniques? According to current cosmology, ordinary matter we know comprises only 5% of the total universe. The remaining 95% consists of mysterious things called dark matter, 27%, and dark energy, 68%. Dark matter is matter that exerts gravity but doesn't interact electromagnetically. It neither emits nor absorbs light, so it can't be directly observed, and its existence can only be inferred through gravitational effects. Dark energy is even more mysterious. It's assumed to be energy with repulsive force that accelerates cosmic expansion, but its nature is completely unknown. It's similar to the cosmological constant Einstein introduced and then retracted. But do these things really exist? Or are our theories fundamentally wrong? Doesn't saying 95% of the universe is unidentified mean we know almost nothing about the universe? The basic theory of current particle physics is called the Standard Model. This theory systematizes fundamental particles that constitute matter and particles that carry forces. The Higgs boson was discovered at CERN in 2012. The theory that the Higgs field, spread throughout the universe, gives mass to particles was confirmed. But this explanation also doesn't answer fundamental questions. Why does the Higgs field exist? Why do some particles interact strongly with the Higgs field to become heavy, while others interact weakly to become light? Why don't photons interact with the Higgs field at all, having no mass? The Standard Model has achieved many successes, but still has many unsolved problems. First, why do exactly these particles exist? Second, why are there 3 generations of particles? Third, why are matter and antimatter amounts different? Fourth, why do neutrinos have mass? Fifth, what is dark matter's identity? To find answers to these questions, string theory, supersymmetry theory, extra dimension theory, etc., are proposed, but they're all speculations without experimental evidence. Even the most powerful current particle accelerator, the Large Hadron Collider, hasn't revealed the universe's fundamental secrets. To build a more powerful accelerator might require a size encircling the entire Earth. A more fundamental question is why matter itself exists. The question philosopher Leibniz raised: why is there something rather than nothing? Physics can explain how matter behaves, but can't explain why it exists. Big Bang theory also starts with the premise that matter and energy already exist. The universe's basic physical constants are tuned with amazing precision to allow life's existence. To explain such precise tuning, anthropic principle or multiverse theory are proposed, but these are also unverifiable speculations. Here, let me add a somewhat cynical perspective. Modern physics has built extremely sophisticated mathematical systems, but this doesn't mean understanding reality. Mathematical models matching experimental results doesn't mean those models explain reality itself. Richard Feynman also said, "Nobody understands quantum mechanics." Even a Nobel Prize-winning scientist confessed he doesn't understand his field of study. What's more problematic is the scientific community's attitude of not acknowledging these limitations and acting as if they know everything. Acknowledging uncertainty and ignorance would be a more scientific attitude. Also, the scientific community invests astronomical budgets in unverifiable theories. String theory research alone has engaged countless scientists for decades, but hasn't produced a single proper experimental prediction. This is closer to mathematical philosophy than science. If we don't understand matter's most basic characteristics, shouldn't we be more humble about how all this came to exist? Matter's very existence is miraculous. Protons and neutrons combine with exactly appropriate forces. Electrons maintain exactly appropriate energy levels, and all physical constants are precisely tuned to allow life's existence. The material world is much more mysterious and complex than we think. From the most basic particles' properties to the entire universe's structure, everything is full of mysteries. We don't need to deny modern science's achievements, but we should acknowledge science's limitations and have humility that there's much more we don't know. Especially matter's very existence and its precise design are too amazing to explain by chance. This could be powerful evidence suggesting a creator's existence. Chapter 5: Dimensional Limitations The arrogance of three-dimensional humans. Humans are beings existing in three-dimensional space. We can only perceive the world in three dimensions: length, width, and height. Even including time as a fourth dimension, our cognitive abilities are extremely limited. To understand what dimensions are, let me give a simple example. A point is zero-dimensional. It has no size or direction. A line is one-dimensional. It has length but no width. A plane is two-dimensional. It has length and width but no height. Space is three-dimensional. It has length, width, and height. Let's imagine hypothetical beings existing only in a two-dimensional plane. These flatlanders can only move forward, backward, and left-right, completely unable to understand the concept of up-down. If a three-dimensional sphere passed through the plane, how would it appear to flatlanders? First appearing as a point, then becoming a gradually larger circle, reaching maximum size, then shrinking back to a point before disappearing. Flatlanders couldn't understand this phenomenon. Just as we, living in three dimensions, can see a sphere's entire shape at once, four-dimensional beings could perceive reality in ways we can't understand. Three-dimensional limitations. Just as beings trapped in two-dimensional planes can't understand three-dimensional spheres, we trapped in three dimensions may be unable to understand higher-dimensional reality. All phenomena we observe may be mere shadows of higher-dimensional reality. Think of Plato's cave allegory. Prisoners trapped in a cave think shadows cast on walls are reality. But there are actually entities casting those shadows. We too may be seeing only shadows of higher dimensional reality. Higher dimensional concepts are also important in modern physics. According to string theory, the universe actually consists of 11 dimensions. Besides the 3 spatial dimensions and 1 time dimension we perceive, there are 7 additional dimensions. Why aren't these extra dimensions visible? String theory explains they're compactified. That is, they're curled up so small we can't detect them. A garden hose looks like a one-dimensional line from far away, but up close you can see its surface is two-dimensional. Similarly, space we perceive as three-dimensional may actually have more dimensions. In the 1920s, Kaluza and Klein proposed a theory that adding one dimension to four-dimensional spacetime could unify gravity and electromagnetic force. This became the beginning of higher dimensional physics. M-theory, which unifies various string theory variations, assumes 11 dimensions. According to this theory, our universe may be a brane floating in higher dimensional space. But these higher dimensions can't be directly observed and can only be inferred mathematically. There's no experimental evidence yet. Viewing light speed as the universe's absolute limit may also be a limitation of three-dimensional thinking. We think light speed is maximum because we only consider movement in three-dimensional space. But in higher dimensions, completely different movement methods may be possible. The shortest distance between 2 points in a two-dimensional plane is a straight line. But in 3 dimensions, you can fold the plane to bring 2 points close together. Wormholes, or hyperspace concepts, frequently appearing in science fiction, may not actually be impossible, but simply higher dimensional phenomena we can't understand. Wormholes, called Einstein-Rosen bridges, are mathematically possible solutions in general relativity. Space-time could curve so distant points connect. In three-dimensional space, to move between 2 points, you must pass through all points between them. But in higher dimensions, this could be different. For an ant to move between 2 points drawn on paper, it must follow the paper's surface. But we three-dimensional beings can fold the paper to make the 2 points touch. Similarly, things we think impossible may be possible for higher dimensional beings. We experience time as flowing one way from past to future. But this too may be a limitation of three-dimensional beings. Most physics laws are symmetric with respect to time. That is, processes from past to future and from future to past are equally possible. Then, why do we feel time's directionality? According to Einstein's relativity, time and space form unified spacetime. From this perspective, all temporal events exist simultaneously. Past, present, and future all exist equally. Our feeling of time's flow may be due to three-dimensional being constraints. Like a leaf floating downstream feeling water's flow, we may experience time's flow while moving in a specific direction through four-dimensional spacetime. For higher dimensional beings, time may be a freely movable domain like a spatial dimension, just as we move freely forward-backward, left-right, up-down. Higher dimensional beings could move freely between past and future. When the Bible says God is Alpha and Omega, beginning and end, this can be understood from this perspective. For beings transcending time, all time could be present. All our knowledge is obtained through the five senses. But our senses are very limited. How many phenomena can't we perceive? Ultraviolet, infrared, radio waves, X-rays, gamma rays can't be detected at all without mechanical help. Our brains are also optimized for three-dimensional environments. Visualizing or understanding four-dimensional figures is extremely difficult. We can calculate mathematically, but can't understand intuitively. Our language is also based on three-dimensional experience. To explain higher dimensional phenomena, we must rely on analogies or mathematics. But analogies are incomplete, and mathematics is abstract. Can we three-dimensional beings fully understand higher dimensional universes? All our observations and theories are based on three-dimensional perspectives. Many problems in current cosmology could stem from dimensional limitations. Dark matter and dark energy, the universe's flatness problem, horizon problem, etc., could look different from higher dimensional perspectives. Big Bang theory could also be a product of three-dimensional thinking. The concept that the universe started from a point and expanded is based on experience in three-dimensional space. But in higher dimensions, expansion could have completely different meaning. The cosmic expansion we see could actually be a projection of other phenomena in higher dimensions. Here, let me add a somewhat cynical perspective. Human science occurs within three-dimensional being limitations. We build theories based only on directly observable phenomena and apply those theories to the entire universe. This is like people trapped in caves trying to explain the entire outside world based only on shadows cast on walls. What's more problematic is not acknowledging these limitations and believing that three-dimensional observations and theories alone can explain everything. This scientific community arrogance. Even theories like string theory or M theory that assume higher dimensions remain in mathematical abstraction without actually experiencing higher dimensions. Science education also doesn't teach these limitations. Students are taught current theories as if they were complete truth. Human cognitive limitations or dimensional constraints are rarely mentioned. Chapter 6. Toward a New Paradigm. According to Thomas Kuhn's The Structure of Scientific Revolutions, science develops not through gradual progress, but through paradigm shifts, when anomalies that can't be explained by existing paradigms accumulate. Eventually, a shift to new paradigms occurs. A paradigm is a system of basic beliefs, assumptions, and methodologies shared by scientists. This determines what problems scientists will study, what methods they'll use, and what answers they'll accept. For example, in the geocentric paradigm, Earth was the universe's center, and all celestial bodies orbited Earth. Within this paradigm, scientists tried to explain planetary movements by creating complex epicycle theories. But as observational technology developed, anomalies accumulated. Venus's phase changes, Jupiter's moons, stellar parallax absence, etc., were difficult to explain with geocentrism. Eventually, a shift occurred to Copernicus's heliocentric paradigm. Such anomalies are accumulating in current cosmology too. A truly scientific attitude is humility, acknowledging that we don't know much more than we do know. Especially problems like the universe's origin or life's origin are areas difficult to verify experimentally. We should be even more humble in such areas. Theories' uncertainties should be honestly expressed. Expressions like estimated to be or likely to be should be used, and alternative interpretations should also be presented. The same applies when introducing science to the public. Theories, limitations, and uncertainties should be honestly stated. We shouldn't speak as if we know everything. Environments should be created where various hypotheses can be studied simultaneously. Studying only mainstream theories while excluding alternative theories hinders scientific development. Creationism, design theory, multiverse theory, plasma cosmology, etc. Various perspectives should be able to compete fairly. Only then can we get closer to genuine truth. Humans aren't beings made only of reason. Emotion, intuition, and spirituality are also important means of cognition. True knowledge should be holistic knowledge integrating all these elements. Here, let me add a somewhat cynical perspective. Current scientific community structure is designed to maintain vested interests. Researchers supporting mainstream theories monopolize research funding, control academic journals, and determine curricula. This is no different from medieval church power structures. Just as the church claimed to monopolize truth then, the current scientific community claims to monopolize truth now. Just as Galileo challenged church power, courage to challenge scientific power is needed now. But current Galileos are being suppressed not by religion, but by scientific vested interests. The scientific community claims to be objective and rational, but is actually very biased and dogmatic. They don't allow criticism of their theories, while indiscriminately attacking religion. Conclusion. Toward true light. Through our long journey, we've examined current cosmology's limitations. Through light speed-based observations' fundamental limits, time and distance measurement uncertainties, ignorance about matter's essence, three-dimensional thinking limitations, etc. We've seen how much current science depends on assumptions and speculation. We can know almost nothing about the universe's current state. Everything we observe is only information from the past, and even that is only possible through light, a limited means. Accurately measuring cosmic distance and age is currently impossible. Too many assumptions and inference steps are involved, so errors inevitably accumulate. We don't properly understand matter's most basic characteristics either. Gravity's identity, electromagnetic force's essence, strong nuclear force mechanisms. Everything remains mysterious. We three-dimensional beings, trapped, may be unable to understand higher dimensional reality. All our observations and theories are based on extremely limited perspectives. The materialist paradigm currently dominating the scientific community has reached its limits. Too many anomalies have accumulated, and it can't provide answers to fundamental problems. A new paradigm should acknowledge design and purpose. Science should be reconstructed from the perspective that the universe and life were intelligently designed. Attitudes humbly acknowledging science's limitations and cooperating with other knowledge domains are needed. Holistic knowledge integrating science, philosophy, and theology should be pursued. Here, let me add a final cynical perspective. What the modern scientific community fears most is their authority being challenged. They're afraid their materialist worldview built over hundreds of years might collapse. But true scientific spirit is doubting and re-examining everything. There should be no sacred areas. No theory, no authority should be exempt from criticism and verification. Just as Galileo said, "Yet it moves," we need courage to say, "Yet God exists." If scientific evidence points to a creator's existence, we need courage to acknowledge it. Don't succumb to scientific community bias and pressure. Have courage to pursue truth. Truth isn't determined by majority vote, nor forced by authority. Genesis 1:3 says, "And God said, 'Let there be light,' and there was light." This light isn't simple physical light. It's fundamental transformative power, changing chaos to order, ignorance to wisdom, darkness to brightness. The physical light we depend on is limited. It only conveys past information and shows only part of reality. Moreover, even that light can be distorted and altered. True light is knowledge's light. But human knowledge also has limits. We only know parts and can't grasp the whole. A higher dimension of light is wisdom's light. This isn't simple information accumulation, but insight recognizing reality's meaning and purpose. The most fundamental light is spiritual light. This is light coming from relationship with the Creator, illuminating existence's ultimate meaning. This entire inquiry shouldn't remain merely academic interest. It should bring actual changes to our lives and worldviews. We should realize how little we know and become humble. We shouldn't absolutize or idolize scientific knowledge. We should have open minds to new possibilities, breaking free from existing preconceptions. We should seriously consider the Creator's existence possibility. We should engage in holistic thinking, integrating science and faith, reason and intuition, material and spiritual. We have responsibility to share knowledge and insights we've gained with others and contribute to society's development. We should have awe before cosmic mysteries and life's wonders. We should acknowledge the possibility that everything might be the Creator's work, not products of chance. The journey pursuing true light is endless. We must continue seeking deeper truth. Science should move beyond materialism's limitations toward more comprehensive reality exploration. Consciousness, information, purpose, meaning, etc., should be seriously addressed. Education systems should also change. Various perspectives should be taught, critical thinking developed, and possibilities for harmony between science and faith shown. Society as a whole should move away from scientific omnipotence toward more balanced worldviews. Science is important, but isn't the only source of truth. Ultimately, spiritual awakening is needed. We should restore relationship with the Creator and realize our existence's true meaning. Closing. Let there be light. Through this long exploratory journey, we've reached an important conclusion. The cosmic view presented by modern science is incomplete and problematic, but the creation story presented in the Bible achieves amazing harmony with scientific discoveries and provides better explanations for the universe's and life's origins. The universe isn't a product of chance. It's not the result of purposeless evolution. The universe is an amazing work designed with wisdom and purpose by an almighty creator. Earth isn't an insignificant planet on the universe's periphery. It's a specially chosen stage by the Creator, a precisely tuned foundation where humans can inhabit and explore the universe. Humans aren't accidental products of evolution. They're special beings created in God's image, endowed with abilities to relate to the Creator and explore the universe's meaning. Light isn't simple electromagnetic waves. It's the Creator's creative power making order from chaos, brightness from darkness, meaning from meaninglessness. Let there be light isn't a simple creation command. It's an ongoing revelation process, an eternal calling leading us to truth. We too should receive that light and convey truth to those in darkness. We should shine the Creator's light on those wandering in scientific omnipotence's darkness. Current darkness and chaos aren't eternal. Truth will ultimately triumph, and the Creator's glory will fill all earth. Until then, we must continue pursuing true light. With humble hearts, open spirits, without losing passion for truth. As Psalm 36:9 says, "For with you is the fountain of life. In your light we see light." This is the true light we should pursue. Eyes that can see everything anew in the Creator's light. This is what's most needed. I sincerely thank you for joining this long journey. It was an honor to explore cosmic and creation mysteries together and share passion for truth. I hope we'll continue the journey pursuing true light together. If you'd like to share more insights and realizations, please subscribe to our channel and set notifications. Your comments and thoughts are also valuable resources. Please share opinions anytime and contact us with questions. I pray this small exploration helps your journey toward truth and that we can feel awe together before the Creator's amazing work. May God's blessings be with you.